Okay, so we're back to solve some physics problems in two-dimensional kinematics. Today we're going to do a problem in projectile motion. Projectile motion problems take on many different forms and many different shapes, but the analysis for all of them roughly follows the same strategy. So today we're going to do a problem which has only half of the classic projectile motion problem to it. So this is the problem we're going to solve. As you know, I am an avid movie buff, so let's do a problem about the movie Tremors. In the movie Tremors, the graboid, which is the monster in the movie, emerges horizontally out of a cliff face at a speed of 5 meters per second, 25 meters above the ground. And what we want to know is how long is the graboid, the monster, airborne? How far from the cliff base does it land? And what are the components of the velocity when it does land? Now, this is a very typical problem that you see when you see two-dimensional kinematics, and in particular when you see projectile motion. There are things in this problem that you have to make assumptions about. And in particular, there are keywords that should guide you towards information that you need to write down in order to solve the problem. For instance, it says that the initial motion of the object that we're interested in is horizontal. So that means initially the vertical speed is 0. Now, most projectile problems are done in the presence of gravity, and so in this case the acceleration in the vertical direction is the acceleration due to gravity, but nowhere in the problem do they say that there's any acceleration in the horizontal motion. And so in those cases, the assumption is that the horizontal acceleration is 0. Since acceleration is a change in speed with respect to time, that means that the speed in the horizontal direction is constant. Okay, so that's the statement of the problem. Let's go about solving it. So the first thing I always do is I draw a picture. So in this case, we have a picture which has a cliff face of known height. The cliff face is 25 meters high. I am free to choose my coordinate system, so I'm going to choose the plus y direction up, and I'm going to set 0 meters at the base of the cliff. Now the graboid, which is this little monster from Tremors, emerges from a height, an initial height, of 25 meters, and then it follows a trajectory that is just like the trajectories we've encountered in projectile motion. It is a downward shaped parabola. Okay, and one of the things that we're asked to find is what is the final distance x where the graboid impacts the ground. Okay, so that's all the information that we're told. So the next thing I do is I set up my kinematic table. Now this is a two-dimensional problem, so I'm going to set up two kinematic tables. One for the horizontal motion and one for the vertical motion. So I start by writing out my kinematic variables. There's x, x naught, vx, v naught x, ax, and t. And my kinematic variables in the y direction are y, y naught, vy, v naught y, ay, and again the time t. Now, as we've talked about before, in two-dimensional motion, the problems are almost always stated in such a way that the time in the problem is common between both the horizontal and the vertical direction. And so the time variable in my kinematic table is actually the same on the x side and the y side. And in fact, this is one of the things that we don't know. So I'm going to put a question mark there for time. And I will draw my usual equal sign that goes across the x and the y boundary so that I know what it is. Okay, as we said when we were reading the problem, the acceleration in this case is the acceleration due to gravity. Because of the way I've set up my coordinate system, the down direction is negative. Since the acceleration due to gravity is pulling things in that direction, we're going to say that the acceleration due to gravity is minus 9.80 meters per second. The graboid emerges horizontally, so its initial y speed is 0 meters per second. We don't know what the final y speed is. Y naught is the initial y coordinate that it emerges from. We said that was 25 meters. And y final is the y position where it ends, and that is at y equal to 0 meters. Okay? So that's the vertical information. Now let's look at the horizontal information. It emerges at x equal to 0, so 0 meters is the initial x position. We don't know the final x position. That's one of the things that we're asked to find. Vx is the speed that it emerges from the cliff face. That is 5 meters per second, and it is the same as the initial speed because the acceleration we decided was 0 meters per second per second. Okay, so that's our entire kinematic table. I can now write out the kinematic equations. There are, in fact, two sets of kinematic equations, but let me just write it out for x. So there is x is equal to x naught plus v naught t plus a half at squared. Vx is equal to v naught x plus axt. I should have had an x subscripts up here on the x and the ax. And then finally, vx squared is equal to v naught x squared plus 2a sub x delta x. Okay, so those are my kinematic equations. There's an exactly equivalent set that's just written in terms of the y variables. Okay, so now we need to figure out what it is that we need to do in order to solve this problem. Now, almost always in all of these problems, the thing that you really will find most useful is the time. If you can find the time somehow, then that's always the first thing that I do. And in this case, I know almost everything I need to know in terms of the y motion in order to find time. So let's take a look at the kinematic equations. Okay, so the first kinematic equation and the second kinematic equations are the only ones that involve time. And if I look at the second one, I see that I can't use it to find time in this case because I don't know time and I don't know the final velocity. So that equation is not going to be useful for me. So in fact, we do have to use the first one. If I write that out for y, it looks like y is equal to y naught plus v naught yt plus a half ayt squared. Now, fortunately for us, we have a few things here that are going to go to 0. In particular, the final position is 0 because it hits the ground, and the initial speed is 0 because all of the motion initially when it emerges from the cliff face is horizontal. Okay, so that being the case, I can now solve that equation for time. So I see that minus a half ayt squared is equal to y naught. And if I solve for t, that tells me that t is equal to minus 2y naught over the acceleration in the y direction, all to the 1/2 power. Now, when you see an equation like that, you've done some little bit of algebra, and you may wonder right away whether or not you've done your algebra correctly or not. Now, one way to check is to put some numbers in and to physically see if the answer makes sense. But you may have a little bit of misgiving staring at this equation right now because of this minus sign that appears under the square root. Well, in this case, I'm not too worried about this minus sign because if I go back to my kinematic table, what I see is that I've already assigned a minus sign to the acceleration due to gravity here. And when I plug that minus sign in for the acceleration in the y direction, those two minus signs will cancel, which will leave the inside here positive, and the square root of a positive number is no problem at all. Okay, so I'm going to go ahead and put in my numbers here. So t is equal to minus 2 times the initial y position, which is 25 meters, divided by minus, so that'll turn that minus into a plus, 9.80 meters per second squared, all to the 1/2. If I look at the units here, I see that the meters are going to cancel and I'll be left with units of seconds squared inside the square root, which when I take the square root will be seconds, which is exactly what I expect for time. And so if I work that out, I find that the time is 5.10 seconds. So that is the time that it takes from the moment the monster emerges from the cliff face to the time that it impacts the ground. Okay, so great. Now that I have the time, I can go on to answer the question of how far is it that the creature actually travels. In order to do that, I'm going to go ahead and employ the position kinematic equation again. In this case, all I'm interested is in the x direction. I was asked to find how far away from the cliff face does it actually impact. And so I'm going to use the position kinematic equation. That's x is equal to x naught plus v naught x times time plus 1/2 ax t squared. Life is good here because there are several things that go to 0. In particular, the initial position is 0. It starts at the origin in terms of x, and the acceleration in the x direction is also 0. So this is really just a problem of multiplying speed times time. And so if I do that, I find that x is equal to the x speed, which is 5 meters per second, times the time, which I found in the part up here to be 5.10 seconds. Meters per second times seconds is meters, which is a distance, so that's good. That's exactly what I expect. And we find that the creature lands 25.5 meters from the cliff face. Okay, so we're cruising right along. This is very typical of what happens in two-dimensional kinematics problems. It starts out having to organize a tremendous amount of information, but as you begin to find things, then it becomes easier and easier to calculate the values that you need to find. Okay, so finally, we need to find the velocity vector, which is we need to find the components. So that's easy enough from the kinematic equations. In the x direction, the speed never changes. So that means that the x component of the final speed is simply equal to the initial x speed, which we were told was 5 meters per second. Great, we're halfway there. In order to find the y component of the speed, I use the kinematic equation for Vy, which is V naught y plus Ay times t. V naught y in this case is initially 0 as part of the problem statement. And so I'm left with the acceleration in the y direction, which is minus 9.80 meters per second, times the time in the problem, which is 5.10 seconds. And if I work that out, I find that the speed in the y direction is minus 50 meters per second. Okay, so at this point, I'm actually done. I've found both of the component velocities that I was asked to find, although often you will see it written as the velocity vector. So let's go ahead and do that for practice. The velocity vector is the velocity in the x direction times x hat, the unit vector that points in the x direction, plus Vy, y hat, the unit vector that points in the y direction. And so this ends up being 5 meters per second x hat minus 50 meters per second y hat. Okay, so that's the complete kinematic solution for the projectile motion of the monster emerging from the cliff. Again, this is very typical of projectile problems. It's exactly half of a projectile problem that goes up and then comes down again, and we'll encounter that in some other examples. Okay, good luck. I'll talk to you again soon.